Welcome to Maths with EJD. I've been making a series of videos on matrices, and starting from the last video, I started considering solving systems of linear equations. In that video, we used the Cramer's rule to solve systems of linear equations, but in this case, we are moving to another method, which is called the matrix inversion method. And as the name implies, it's all about finding the inverse of a matrix to get the solution to our system of equations. So just as an example, you have this sample given a 2 by 2 matrix, a 2 by 2 system like you have the A11x plus A12y equals B1, and then A21x plus A22y equals B2. Of course, you are looking for x and y. So in that last video, also I explained to you how to make a system like this into a matrix. So, and this is what exactly you have here. So you have the first matrix A, which is actually the collection of the coefficients. That's A11, A21 for the coefficients of X, A12, A22 for the coefficients of Y. And of course, you have the variables X and Y. So if you multiply this out, you end up getting back here. And of course, the right-hand side is also in form of a column vector like the like for the variables, right? So this is what I would always refer to as the right-hand side. Okay. So now if you are able to put your system into matrix form like that, the next thing you can see that this matrix has three parts. It has the matrix of coefficients, which we would always call A. Then it has a column vector, which you can call X. That's this what you're actually looking for, right? And B1 is the right-hand side. So generally speaking, you can say that every matrix like this that is represented in this matrix form can be represented as AX equals B. AX equals B. And because you have AX equals B now, AX equals B, you have AX equals B, and you're looking for X. So since you are dealing with matrices, normally, if you're dealing with any normal number, you should have just said divide both sides by A, right? You have, AX equals B, and then, okay, let's assume you are dealing with AX equals B, and A and B are just, numbers. So you just divide through by A. So you have AX over A equals B over A. This cancels out, and then X is equal to B over A, or what you can call A inverse multiplied by B. You can have that for normal numbers. But here, you're dealing with matrices, so you have to treat it as a matrix. So you're technically doing the same, you're dividing both sides by A, right? But the approach is different. Since you're dealing with matrices, the way to nullify a matrix is to multiply the matrix by its inverse. If you remember, if you multiply a matrix and its inverse, so you get a unit matrix. So for instance, you have A. So you want to nullify this A now. So you can say A inverse, multiply both sides by A inverse. So you have A inverse A. Of course, the X remains there. And then you have A inverse B. So this A, of course, maybe I shouldn't even be that fast. A inverse A will give you a unit matrix, then multiplied by X, which is equal to A inverse B. And the unit matrix is like the one in terms of matrix. So it's multiply 1 by X. You end up getting your X, which is A inverse B. So basically in this place, this is what the kind of thing we are always dealing with. So you are looking for X, which is the product of the inverse of the matrix of column of coefficients multiplied by the right-hand side. Basically, that's this fundamental thing about matrix inversion method, So generally speaking, under the matrix inversion method, you have a system, you make it into a matrix. Of course, you express it algebraically this way, and then you can also express it this way. So fundamentally, we are looking for the solutions, which is expressed as the inverse of the matrix of coefficients multiplied by the right-hand side. And that is what this is about. So let's get into some actual questions and see how things go. So I'm starting with a 2 by 2 matrix as usual. I guess it's the same matrix I solved in the other video, in the video preceding this. So here we want to solve 2F plus 3G equals 8. 4f minus 2g equals 6 using matrix inversion. Using matrix inversion, of course, like you know already, you have 2, 3. That's what we have here. You have 4 minus 2. Don't throw away the minus. If not, things will be wrong. So that's what you have right there also. Then you have FG, right? That's your column vector for the variables. And you have 8, 6. That is your column vector for the right-hand side. And this is A, this is X, and this is B. So, and what are we looking for? We are looking for X, which is equal to A inverse B, basically. So that's the setup. So the most important part of matrix inversion method is looking for the inverse. Looking for inverse can be quite a task. And I've already explained 2 methods for looking for the inverse of a matrix. The first one was the minors and cofactors method, and the second one was the Gauss-Jordan method, where you augment the matrix with a unit vector, and then you do elementary row operation until the first matrix becomes a unit vector, and the second one becomes something which is actually the inverse of the matrix whose inverse you're looking for. Okay, in this case, I'm using, so you're at liberty to use any of the methods for finding inverse that you like. So for this one, I'm using the Gauss-Jordan method. And for the Gauss-Jordan method, what we do is this matrix of coefficient now, you augment it with the unit vector corresponding to it. It's a 2 by 2 matrix, so you need a 2 by 2 unit vector, So that's why we have this now. So we want to find A inverse using the Gauss-Jordan method. So we have this augmented, this is the matrix of coefficient, this is a unit vector for starters, that's A and I, like we already know. And then the purpose is to change this into a unit matrix and change this alongside it, so that at the end of the day, this one becomes something and this one becomes unit vector. And then we know that whatever this becomes is that inverse of A. Okay, so now we know that at the end of it all, to get to where we are going to, we need to do the reduced row echelon form. The reduced row echelon form. That is what turns this one into a unit vector. So that's the reduced row echelon form. And what that simply implies is that at the end of the day, if using the reduced row echelon form, right? At the end of the day, what you're expected to have is 2 here, 1 here, 0 here, 1 here, and 0 here. That's the rule, this 2, 1, 1, and 2, 2, they are the pivots, they are the lead entries. So they should be 1, and then the other entries should be 0, basically. So that's the idea. And that's what we are aiming at, to make this one 1, to make this one 1, to make this one 0, and to make this one 0. Okay, so how do we pull that off? So we go on with elementary row elementary row operations, and it all involves, you can swap, you can swap rows, you can scale rows by multiplying with any number of your choosing. You can also do some summing and subtracting of columns, multiples of rows, sorry, not columns in this case. Of course, you can do the same thing for columns, but in that case, everything will be strictly focused on columns. So let's go. So I suggest that you do this column by column. So take this column first, settle it. Once you do that, then move to the next one. So to settle this column, there are 2 things we need to do for this column. We need to make this 1 and we need to make this 0. And for me, the way I easily want to do that is, it's easier for me to just make everything 1 and then subtract. Easy. So, and that's why I always like this approach. You don't have to do this. There are other ways of doing it, but I find this one more comfortable for me. So in that case, we have to make this one 1. So the new row 1 is going to be half of the old row 1. So half of the old row 1 becomes our new row 1. And then because this one, I also want to make it 1 to make it easy for me to subtract. So I say 1/4. Of course, to make this one, I need to multiply it by its multiplicative inverse, which is 1/4. So 1/4 of the old row 2 gives us the new row 2, So let's do that. So you see that half times 2 is 1, half times 3/2 is 3/2, half times 1, half times 0 is 0, settled. Then 1 over 4 of old row 2 becomes the new row 2. So 1 over 4 is 1. 1 over 4 of minus 2, that's minus 2 over 4, that's minus 1 over 2. 1 over 4 times 0 is 0. 1 over 4 times 1 is 1 over 4. So that is achieved. So the next thing is, since we have achieved this one, we need to make this one into 0. So, and now that both are 1, it's easy to do that now. So all we just need to do is, since this one is already established, we keep it the way it is. So the old row 1 is still the new row 1, but the new row 2 now is going to be the old row 2 minus the old row 2 minus the old row 1, and you do it across like that. So the new row 2 is the old row 2 minus the old row 1. So that means you have 1 minus 1, 0. Minus half minus 3 over 2, minus half minus 3 over 2. That is LCM is 2. So you have minus 1 minus 3, and that is minus 4 over 2, and that is minus 2. So that's why we have minus 2 here. Then 0 minus half, of course, that's minus half. 1 over 4 minus 0, that's 1 over 4. So now that is accomplished. So then we can think of further issues. So now we have 1, 0 here as expected. So the next thing is, we want this one to be 1 because it is the pivot, but we want this one to be 0. So of course, the first thing I will always like to do, there are other things you can do, but the easiest one, I think, for me and maybe for you, would be just turn all these two elements to 1. And once you turn them to 1, you can now easily subtract. So by turning them to 1, to turn them to 1, you just need to multiply each of those values by their multiplicative inverse. Multiplicative inverse is that number with which you multiply a number to give you 1, because 1 is the identity under multiplication. Maybe one of these is, I'm going to talk about some of those kind of operations where we talk about identity inverse elements and all those. Okay, so now that we have this, we need to move forward. We need 1 here. We also need 0 here. But the one easy way to go ahead with that is to make both 1 first. So to make 3 over 2 1, you can multiply the old row 1 by 2 over 3. And to make this one 1, you can multiply the old row 2 by minus 1 over 2, because this minus 1 over 2 that will turn this one into 1. All right. So that is what we are doing. So 2 over 3 times 2 over 3 times 1. Now, never mind that this one, you want 1 here, but you need to make it something else first. Once you have 0 beside it, it's easy to take it back to 1. So, but for now, we need to achieve this purpose. So you just want to turn this one to 1. So 2 over 3 times, you want to just need 1 here, right? So you need to trample on this for a moment, so that you can come back to it later, make it 1 finally. So 2 over 3 times 1, of course, it will make this one 2 over 3 temporarily. 2 over 3 times 3 over 2, that's 1. 2 over 3 times 1 over 2, that's 2 over 3 times 1 over 2. 2 cancels 2, so you have 1 over 3. That's why you have this 1 over 3 here. 2 over 3 times 0, easy peasy, that's simply 0. Then minus half times 0, that's 0. Minus half times minus 2, that's 1, which is our purpose. Then minus half times minus half, that's minus and minus plus 2 times, then 1 over 2 times 1 over 2, that's 1 over 4. And lastly, minus 1 over 2 times 1 over 4, that's minus 1 over 8. Again, we have achieved that, but of course, at least now, row 2, column 2 is now 0, is now 1, but we need this one to be, this is the pivot, we now need this one to be 0. So now that they are both 1, it's easy to just subtract and get it. So now the new row 1 is going to be the new row 1, R1, is going to be the old row 1 minus the old row 2. So, and then the answer we put for row 1, that's the new row 1. So you have 2 over 3 minus 0. You have 2 over 3 here. 1 minus 1, you put it here as 0. Then 1 over 3 minus 1 over 4, that's 1 over 3 minus 1 over 4. LCM is 12. 3 in 12, 4, minus 4 in 3, 4 in 12, 3. That's 1 over 12. That's why you have this 1 over 12. That's 1 over 3 minus 1 over 4. That's 1 over 12. Then 0 minus 1 over 8. That will be 0 plus 1 over 8, which is 1 over 8. So we have that row. Then row 2 remains because we want it to be we want 0, 1 here. So because what for a 2 by 2 matrix, you just need 1, 0, 0, 1. So it's already 0, 1. So you just leave it the way it is. So you have 0, 1, 1 over 4 minus 1 over 8. And that's what you have here. So that is maintained. So we are gradually getting to our destination. Don't forget the purpose is to make the first matrix into a unit matrix. Okay, so from here now, we see that we have 1 here, we have 0 here. So all we just need to do, the only challenge now is to make this one 1 back. And once we do that, we can arrive. So, and how do we turn 2 over 3 to 1? We just multiply by the multiplicative inverse, which is 3 over 2. So 3 over 2 times 2 over 3 is 1. 3 over 2 times 0 is 0. 3 over 2 times 1 over 2. 1 over 12. 3 over 2 times 1 over 12. 3 here is 1. 3 here is 4. So you have 1 over 8. 1 over 2. That's 1 over 8. 2 times 4, 8. Then 3 over 2 times 1 over 8. 3 over 2 times 1 over 8. This is 3 over 16. And that's why you have 3 over 16 here. 3 over 16. So next, this one, R2 remains R2, so nothing to worry about. So now at this point, you can say that, yes, we have arrived because the A you started with has now become a unit matrix. So this is now a unit matrix, and we want to believe that this is the inverse, Of course, I've taught you the way to check that. Just multiply the inverse by the original matrix and see if it gives you 1. So if you can achieve 1 with that, you're fine. So what I'm just doing, I'm just saying, therefore, A inverse is equal to this, 1 over 8, 3 over 16, 1 over 4, minus 1 over 8. Since 16 is the biggest number, we can take it out. So if you take it out, then, of course, to balance it, 1 over 8, since you've taken 16 out, this will be 2, because 2 over 16 is 1 over 8. Then 3 over 16, of course, that remains because 16 was under it. For 1 over 4, to get for 1 over 4, this becomes, for 4 over 16 is 1 over 4, so the 4 remains here. For minus 1 over 8, this is minus 2, because minus 2 over 16 is minus 1 over 8. So this makes things a bit tidier so that you don't have to stress too much about fractions. So this is the inverse now. But don't forget, you are not just looking for inverse. You are looking for inverse so we can get x. And don't forget where we are coming from. We remembered that x was given as A inverse B, like this. X was given as A inverse B. So, and now that we have A inverse to be 1 over 16 into 2, 3, 4 minus 2, and don't forget B, the right-hand side is 8, 8 and 6. And like I taught you, of course, this is constant. You see, it's very good to bring it out, because if you left it as fraction, you would have to be multiplying with fraction all the way. So it's good that this one is outside, chilling, waiting for what is going to come next. And of course, if you remember, if you want, like I told you, if you want to multiply matrices, this is a 2 by 2 matrix to be multiplied by a 2 by 1 matrix, which is possible because once the number of column of the first is equal to the number of row of the second, then it is amenable to multiplication. And you are going to end up getting a 2 by 1 matrix, 2 by 1 matrix. That's 2 rows, 1 column. So in that case, since you have 2 rows in the first one, you have 2 rows here. So that means you're going to write this 8, 6 twice. So you have 8, 6, 8, 6. And then you're going to invert 2 over 3 on the first one. You're going to invert 4 minus 2 on the second one. Then you say 8 times 2, 16, plus 6 times 3, 18. So 16 plus 18, that's 34. And then 8 times 4, 32, minus 6 times 2, 12. That's 32 minus 12, that's 20, And then don't forget, you have 1 over 16 outside waiting. And then f of g now will be equal to 34 over 16, 20 over 16. 34 over 16 is 17 over 8. This is this. And 20 over 16 is 5 over 4. And I think this is the same example we did in the previous video. And we got the same f now. So this, your f is 17 over 8. And g is 5 over 4. So you have f is 17 over 8. G is 5 over 4. So the most difficult part is to get the inverse. And once you get the inverse, you multiply by the right-hand side and you get your answer. So that is that for this particular question. So let's look for a 3 by 3 case, which of course promises to be not as easy because we are looking for inverse. All right. So this is what you have here. So example 2 now, I think it's the same example like in the second video for 3 by 3. So again, we are looking for a plus 2b minus c equals 5, 2a minus b plus 3c equals 12, 3a plus 4b plus 2c equals 20. And then, of course, it's easy to just convert it into a matrix form like this. Just pick the coefficients, 1, 2 minus 1 for the first one, 1, 2 minus 1 for the first one, 2 minus 1, 3, 2 minus 1, 3 here. Then 3, 4, 2, 3, 4, 2 here. And then you have ABC, the column vector, and the right-hand side, 5, 12, and 20. That's easy. And then you know that this matrix of coefficients is your A. This ABC, this column vector is your X, which you're looking for, and the right-hand side is B. And we know to get X, you just take the inverse of both sides, and you get X equals A inverse B, like this. So, and the biggest task, like I keep saying, under matrix inversion method is to find the inverse of the matrix of coefficients. So, the other time I used the Gauss-Jordan method. Now, let's see, I want to use the minors and cofactors method. So, to explain to you that you can use any method you choose as it's convenient for you. Okay. So don't forget the matrix of coefficients is 1, 2 minus 1, 2 minus 1, 3, 3, 4, 2. So we are looking for the inverse. And for the minors and cofactors method, you need the determinant, you need the minors, you need the cofactors, and then you need the inverse of the cofactors, which is the adjoint, and then the inverse, A inverse here is actually the adjoint of A all over the determinant of A. Okay, don't forget that. So so the first thing we are looking for now is the determinant. The determinant of A, this is just a sign plus, minus, plus as usual. So you have plus 1 into cross this out, you have minus 1, 3, 4, 2 here. Then again, you go for minus 2. You have minus 2 here, and then cross the column, cross the row. You have 2, 3, 3, 2 here. And then lastly, you have plus minus 1. Plus minus 1 is plus minus 1. Plus times minus is minus, so you have just minus 1. And then cross the column, cross the row. You have 2 minus 1, 3, 4, 2 minus 1, 3, 4. Okay, now we tidied things up a little bit more. And then we have, okay, we tidy things up a little bit more. So you have plus 1 into minus 1 times 2, that's minus 2, minus 2 minus 12, because 3 times 4 is 12. So minus 2 minus 12, that's minus 14. Then minus 2 here, 2 times 2, 4, 4 minus 9, minus 5. Then minus 1 into 2 times 4, 8, minus 3, that's 11. So and we have, so this is minus 14, this is plus 10, this is minus 11. So minus 14 plus 10, that's minus 4. Minus 4 minus 11, that's minus 15. So this is settled. So that's us getting the determinant. So the next thing we need to find would be the minors of A. Now, the minors of A is a very interesting concept. So for the minors of A now, it means for each element of the matrix, you are going to find its minor. So you are going to find the matrix of minors. So to get the minor, for this element 1 now, you cross the column, cross the row, you get minus 3, 1, 4. That's what you have here. So for the next one, element 2, for this 2 now, you cross it. The only thing is that for determinant, you needed to multiply by that, but here for minus, you don't multiply by the number. You just cross the row and the column out, and you get 2, 3, 3, 2, and that is what you have here. And then for the next one, you have for the minors of minus, the minor of minus 1 will be achieved by crossing out the row and this column. You have 2 minus 1, 3, 4, and that's what you have here. So the trouble here is that you don't just stop with the first row, you do it for all the elements. So for this 2 now, you cross the column, cross the row, cross the column, you have 2 minus 1, 4, 2. And that's what you have taking its place. So the minor of an element will take the place of that element. Okay, then we have done for 2, we go for minus 1. So cross the column, cross the row, you have 1 minus 1, 3, 2. And that's why you have 1 minus 1, 3, 2 here. Then to find the minor of 3, to find the minor of 3. This is 3. Cross the row, cross the column, and you have 1, 2, 3, 4. Interesting. So you have 1, 2, 3, 4 right here. Okay, so we have one row left. So for minor, you have to find the minor for every element. So 3, cross the row, cross the column, cross the row. You have 2 minus 1, 1 minus 3, and that's what you have here. So next, you need the minor for 4. This 4 now. Cross the row, cross the column, and you have 1 minus 1, 2, 3. 1 minus 1, 2, 3. There. Then you have the last one, which is 2. So this is 2 now. Cross the row, cross the column, and you have 1, 2, 2 minus 1. That's exactly what you have here. So I want to believe that's like the hardest part of this matrix minors and cofactors method. That should be the hardest part, I want to believe. So the next thing is just to tidy things up like we did under determinants, except that we are not multiplying by the numbers we were referencing. So here you have minus 1 times 2, that's minus 2. Minus 2 minus 12, that's minus 14. 2 times 2, 4. 4 minus 9, minus 5. 2 times 4, 8. 8 plus 3, that's 8 minus 3, that's 11. Then, having taken care of that, next row, you have this. So 2 times 2, 4. 4 minus 4, because 1 times 4 is also 4. 4 minus 4, that's 8. That's 4 plus 4. Then 1 times 2, 2, you know. So you have 2 minus 1 times 3. Minus 1 times 3, that's minus 3, right? So you have 1 times 2, 2. Normally, there should be minus. Then you now have minus 1 times 3, that's minus 3. That's 2 plus 3. And that gives you 5. And that's why we have this 5 right here. Then the next one is this. You have 1 times 4, 4. 4 minus 6, that is minus 2. So that's for the second row for the matrix of minors. So let's go on to the third row. So for this now, you have 2 times 3, 6. 6. So now this is tricky, right? 6 minus, you now have minus 1 times minus 1. I think I stumbled on it the first time I did it. So you have 6. So you have to be very careful, especially if you're in an exam condition. So you have 6 minus. So minus 1 times minus 1, that's plus 1, and that is 5. In fact, I got it wrong first because, I mean, you could easily stumble over that. So 6 minus 1 is 5. So watch that. The minus can be a very tricky thing. I remember I lost the maths prize in SS1 in Badagry Grammar School because of a minus in a test. It was so painful. I got 86 in the exam, and the teacher said, a bit disappointing. That was the remark. Okay. So I go to this. 1 times 3 is 3. So be careful of minus. So as much as possible, if you can avoid minus, avoid it by all means. But be careful if you can't avoid it. So you have 3 minus 1 times 2. So that's 3 plus 2, and this is 5, right? So 1 times minus 1, that's minus 1, minus 2 times 2, that's 4. So that's easy. You're owing 1 and you're owing 4. That means you're owing 5. That's minus 5, and that's why you have this. Okay, so I want to believe that's the hardest part of this minors and cofactor method. So now we have our matrix of minors. So we have got the determinant. Now we have got the matrix of minors. And the next thing we want to do is to get the cofactors. Cofactors are pretty easy. Cofactor is just you applying the sign attached to each location to whatever you have in the matrix of minors. So if you come here now, this is row 1, column 1. Normally, don't forget the rule. It's minus 1 raised to power the row number plus the column number. So for 1, 1, that will be 1 plus 1, 2. So that's minus 1 raised to power 2. Of course, that will be positive. But for odd numbers like 1 and 3, so that'll be minus. So that's why this is plus, this is minus, this is plus. And of course, down the column rather, you have minus, plus, down the column, minus, plus, minus, plus, minus, plus. So you have the signs alternating like that. So that's really important to understand. Okay, so cofactor is just you applying those signs, basically. And then you have the cofactor of A now. If you apply the sign plus and minus 14, you have minus 14. Minus 5, you have plus 5. Plus 11, of course, that's 11. Minus 8, good. Plus 5, nice. Minus 2, that's 2. Plus 5, you have 5. Minus 5, you have 5. Plus minus, that's still minus 5. So with that, we have the cofactors, matrix of cofactors now. So now that you have the cofactors, the next thing you want to get is the adjoint. You need the adjoint of A. And the adjoint of A is simply the transpose. It's the transpose of the cofactor of A. So now to transpose, so it means you're just transposing this to get the adjoint. So transpose means rows become columns and columns become rows. So that's why row 1 here, minus 14, 5, 11 becomes column 1 in the adjoint. That's minus 14, 5, 1, 5, 11. Minus 8, 5, 2 becomes column 2. That's row 2 becomes column 2. Row 3, 5 minus 5 minus 5 is the third row there, and in the cofactors, it becomes column 3 in the adjoint. And with that, we also have our adjoint. Easy peasy. The hardest part is getting minus and all that. Okay, so now we have the adjoint of A, and now we have everything. So once you have adjoint and you have determinant, you can get your matrix inverse. So we know that A inverse is adjoint of A over A, and of course that means the adjoint divided by the determinant. Don't forget the determinant we got was minus 15. So we can say this whole thing divided by minus 15, or you can also say minus 1 over minus 15 into the adjoint this way. And then, of course, just like I told you, if you can avoid minus, please try and avoid it by all means. So, but one way of avoiding it here is instead of carrying it along with this 15, just push it inside. And once you push this minus inside, it affects every sign it comes across. So you have 1 over 15. That's why you have to be careful of negative people because it can affect you. Interesting. So we learn wisdom from math, So minus, it can disturb you, so push it inside. So once you push it inside, wherever there's minus, it becomes plus. Wherever there's plus, it becomes minus. So you have minus and minus plus 14. So minus 8, that's plus 8. Minus 5, it was plus, now it's minus. So ordinary normal 5, that's minus 5. Plus 5, now minus 5. Minus 5 before becomes normal 5. That's positive 5. Then positive 11 becomes minus 11. Positive 2 becomes minus 2. Negative 5 becomes positive 5. So push the minus away as much as possible so you can have fewer minuses to deal with. Okay, so now that you have your inverse, don't forget where you're coming from. You need to find X, which is A inverse B. So this is your A inverse, and your B is the right-hand side, 5, 12, and 20. So you have 1 over 15 into 4, 8 minus 5, and all that, So now we need to do matrix multiplication of matrix with column vector, which was one of the first things we did under matrix multiplication. So here, you are multiplying a 3 by 3 matrix. You're multiplying a 3 by 3 matrix with a 3 by 1 matrix, which is possible because the number of column here, the number of column in the first matrix is equal to the number of row in the second matrix. That's a rule for multiplying matrices. And then you're expected to get a 3 by 1 matrix, 3 by 1 matrix. That means you're going to have 3 rows and 1 column. So in that case, all you just need to do now is, I always refer to the number of columns, 1, 2, 3. In that case, you're going to write this one 3 times. So you have 5, 12, 20, 5, 12, 20, 5, 12, 20. And then you put this one's over it. 14, 8, minus 5 for the first one. For the second one, minus 5, minus 5, 5. For the third one, minus 11, minus 2, 5. And then once that is done, you can now multiply and add, So here, 5 times 4 is 70, 12 times 8, I think that's 96. So you have 166, right? And then 20 minus 20 times minus 5, that's minus 100, and you get 66. That's why this place is 66. Okay. So that done, you go to the next row, which is this. So you have minus 5 times 5, that's minus 5 times minus 4, that's minus 25. 12 times minus 5, that's minus 60. So you have negative 85. All right. Then 20 times 5, that's plus 100. That's like 100 minus 85, that's 15. And that's why you have 15 here. Then we go to the third row. for the third row now, you have 5 times minus 11, that's minus 55. Then 12 times minus 2, that's minus 24. So you have minus 79 right there. And then 20 times 5 is positive 100. So that's 100 minus 79, which is 21. And that's how you have that. And now you can take the minus 15 inside. Take the minus 15 inside, you have 66 over 15. That's 3 in 66, that's 22. 3 in 15, that's 5. Then 15 divided by 15 for this, you have 1 here. Then 21 over 15, right? 3 in 21, that's 7. 3 in 15, that's 5. So finally, you can now say your A, B, and C are these values. A is 22 over 5, B is 1, and C is 7 over 5. That's so interesting. And of course, because I want you to also master it, so you can try this out. Try this out as much as you can. Of course, if you have any issues, you can talk to me in the comment section or something. If you need me to do something, also let me know. All right. Interestingly, in this video, I have a bonus for you. I mean, it's just it has nothing. Well, it's something about determinant, right? But it's just it's just an aside, just a bonus. So you want to prove that the determinant of the matrix here is independent of phi. So you know you have x sine phi cos phi minus sine phi minus x1 cos phi 1x. So you want to show that the determinant is independent of phi, that at the end of the day, there's no phi in the final determinant. So you just go through the normal determinant process and all that. At the end of the day, you end up getting minus x cubed. And though you have phi, this is what you call phi. All this sign is phi. It's a Greek alphabet, I think. So at the end of the day, by the time you're done with all the determinants, you get minus x cubed, which has nothing to do with phi. So it means that the determinant actually is independent of phi. So you may just want to try your hands on that and see how that goes. So with this, we come to the end of this video. We see in the next one where I'll still be talking about solving systems of linear equations now using Gaussian elimination and Gauss-Jordan method. So when we get there, we'll talk about that. So see you in the next video. Thanks for always listening.